everything that we talked in the past few weeks, almost the first section of the semester is about conduction. And then convection is a major part of the heat transfer in chemical engineering. Let's look at the a fluid flow on top of a stationary plate. And by the way, at the beginning of the semester, we introduced three modes of heat transfer. Convection is one of them. And the reason why convection is different from conduction is because convection not only have heat transfer, but also the heat transfer is related to the mass transfer, basically related to the movement of the molecules of the fluids. So it only occurs when you have a interface between a fluid and a solid. So if we have a flat plate at the bottom here, and then let's say it's infinitely long, and then we have a flow, water flow coming from the left side at a constant velocity, we call U infinite. And the temperature of the fluid flow is T infinite. U infinite is the velocity and T infinite is the temperature. And then when this flow reached on top of the surface of this stationary plate, we know that the velocity of the fluid at the vicinity of the plate is zero. In other words, immediately on top of that stationary solid surface, the fluid doesn't move. And then as you go further away from the surface, the velocity gets increased and until it reaches the bulk value, U infinite. So this is basically a y-axis. And then this is basically the x-axis, right? And then as you can see, the velocity in the x direction is a function of the y, the location in the y direction. And if we draw a outline of this velocity, the velocity profile looks like this dotted line. And then when the heat transfers, because the temperature of the plate is different from temperature of the fluids, now we introduce a additional temperature parameter. So if this is the surface temperature Ts, then we know the heat transfer will occur in the vertical direction upwards in the y direction. And this Q occurs because the heat is being conducted within the fluids from the surface to the water. So you can imagine, yeah, at the right surface, the temperature of the fluid will be same as the surface temperature. But however, in order for the heat to carry away in the y direction, it has to go across the water. In other words, it's conducted by the conduction of the water. So this is because of the conduction constant by a mode of conduction heat transfer. But however, the difference between conduction and convection is it not only has conduction in the y direction, but also it has the removal of the heat because the water is flush from left to right. So wherever heat will carried upwards, it will be carried away by the water flow, right? So there will be two modes of the heat, two steps of the heat transfer. So this convectional heat transfer rate, this is the convection coefficient. It depends on two things. One is how fast heat goes upward in fluid. And this is conduction of the fluid, which is dependent on the conduction coefficient of the fluid. And in addition, this convection coefficient also depends on the how fast fluid carries away the heat. So how fast the flow moves. And then this is actually by movement. But movement is daily language. In chemical engineering, we use Reynolds number to describe the fluid flow. And then here, a few notes I just put on. So the T infinite is the temperature of fluid. And the Ts is the temperature of surface. And then because I draw the heat traveling upwards previously like this, so the assumption was Ts greater than T infinite. And of course, if it's opposite, it's fine. The Q will have the opposite direction, and then everything else will be same, basically, just a negative sign for everything. So this is the, how to say, the physics picture of the convection. And one thing I want to talk a little bit more detail is the scenario, the similarity between three transfer processes. So one is the shear stress, the momentum transfer. So if we still have this u velocity, then at the beginning, the velocity will be same as the bulk velocity everywhere. And then, however, as the water goes across the surface, this so-called boundary layer is developing. And then, by the way, I forgot to mention this range. This range in the y direction where the velocity develops from 0 to the bulk. So this will be u infinite, and then this is equal to 0. And then this range is called the boundary layer, or boundary region, boundary. And then this boundary develops from the left to right. And then within the boundary, the velocity increases. And then above this boundary, the velocity reach the full scale does not change anymore. So this will be the profile. And then, as I said, this is the boundary. Let me use the word boundary. Boundary layer thickness, we use this delta to represent this. And then outside this boundary layer, it reaches the infinite universal velocity, right? So in this momentum transfer case, what is acting on the plate or acting on the fluid? It's actually the shear stress. The shear stress is proportional is proportional to the change of the velocity. So how fast the velocity changes in the y direction. In other words, how fast it changes from 0 to a positive number. That is proportional to the force that the fluid's acting on the solid plate. And then this slope of that velocity change at y equal to 0, that's right on the surface. And then because it's proportional, and then the ratio constant, it is the viscosity of the fluids. How sticky the fluid is. The more sticky it is, the more forces it will drag on the plate, or the shallower the velocity change will be. And then if we say this is x direction, and then this would be the ux in the y direction. And then if we have heat transfer, and then again, if we say the temperature of infinite is lower than the temperature on the surface, right? So we know that when it's far, far away from the surface, the temperature reaches the bulk temperature. It does not change. But however, when you approach to the surface, this temperature will gradually increase until it reaches the surface temperature. If you draw the outline of the temperature profile, then it will look like that. I use a different color so you can view better. As you can see, the temperature changes at the vicinity of the surface, and then this region before the temperature reaches the bulk, that's called the thermal boundary layer thickness. So it's a thermal boundary layer. And then, of course, if you look at the temperature, it would be T infinite. T infinite. And then if we calculate the heat transfer rate per unit area, by the way, the shear stress is also a unit surface area. And then that is proportional to the temperature gradient at the surface within the fluid. And this is because how fast the heat goes upwards in the fluid, right at the surface. That's how much heat being carried away from the surface. And then the proportional constant, it is the conduction coefficient of the fluid. As you can imagine, this is basically conduction. In fluid. And then this is what happened. This is the equation to describe the physics. And then empirically, that's what we did in the past. We had a convection coefficient times the temperature difference, which is the surface temperature minus the infinite temperature, right? So therefore, if you compare these two equations, you can see the H is actually sort of related to the conduction coefficient of the fluid. And then the temperature gradient at the surface And then also related to the temperature, overall temperature difference. This. And then if you, I mean, more, how to say that, are careful, it's actually, then it's inverse of this guy, inverse of the guy. But anyway, I just keep it related. So this is related to this, okay? I'm not saying proportional. Okay, and then the other transport process related to this fluid is actually mass convection, convectional transport, convectional mass transport. So in other words, if you have a solid that is being dissolved into water, so this plate is a solid that can be dissolved in the water. And then the water itself has a diluted concentration. And then the A is the substance that being dissolved. The cases like this are pretty popular in environmental engineering. So for example, if you are looking at the geology, you have a tunnel, if you have a cave, and if you want to study the CO2 effect, and then this will be the case. So the surface concentration of the substance will be actually, most of the case, it will be saturated. And then, however, far, far, far away from the surface, that will be the bulk concentration. And then when it approaches to the surface, then it will start to increase until it reaches the surface saturation concentration. So if you draw an outline of the concentration profile, it will be like the red color outline. And then, of course, the boundary layer thickness is also defined as this, but this is a mass transport, mass transfer boundary. Then this will be the saturation or surface concentration of the substance A. This will be infinite concentration of substance A. And from the physical understanding, what happens is actually the mass transport in the vicinity right on top of the surface is by diffusion. So therefore, the mass transport flux equals to the concentration gradient at the surface times the constant of the diffusion constant, diffusion coefficient. And then in the empirical method, we also defined a so-called convectional constant for mass transfer, and then for the substance A here. And then it's proportional to the concentration difference between the surface and the bulk. And therefore, same as the heat transfer, we know that if we compare these two, then we know the empirical convection constant is related to the diffusion coefficient of the substance, the concentration gradient at the surface, and the concentration difference between the surface and the bulk. All right, I think that's all I can cover in the video.